Topics for today are, first we will, on the last class we covered evaluation metrics, and kind of like a continuation of that, today we will talk about some practical tips for applying machine learning in practice, especially if you want to build a machine learning model focused on a real world deployment. And with that we're going to finish up all the topics, and we'll spend some time talking about the final exam format, what kind of a final exam structure you can expect in the take-home exam. And then we're going to begin our the full course review, starting all the way from the beginning, giving you an overview of what we've covered in the course so far. We'll be, as part of the course review, we'll be emphasizing more on topics that are more relevant for the exam. And we'll go over both the topics that we covered in the lectures and also discussing related homework problems. So we haven't really had a chance to kind of go over the homework problems in the lecture itself. So we'll be discussing some of the homework problems that we've covered and how they kind of match up with what we've seen in the lectures and how they relate to the lectures and so on. So machine learning for production. So with the algorithms that so far in the course, we've mostly studied algorithms, right? So we've studied different kinds of algorithms, supervised, unsupervised, reinforcement learning. We've looked at some theory, and in the last lecture, we also saw some evaluation metrics. If you're planning to build a machine learning model for some kind of a say a real life product that you say you're building a product for, let's say in your company, say you're working for a company or you want to start a new startup which uses some kind of a machine learning model, the approach that you take towards building a real practical model is somewhat different from the kind of approach you would take for, let's say, building a new algorithm to be published in a research paper, right? And most of the, probably the biggest difference between machine learning in practice and machine learning in research, versus research. The first thing that you would do if you were to deploy machine learning, if you're building a machine learning model for deployment, is to start collecting a dev set. Right? So the first thing you would do before deciding, which model you want to use, it may be logistic regression, it may be, a neural network, what have you. The first thing you want to do is start collecting a dev set. By start collecting a dev set, what we mean is start collecting data that your model is going to encounter when it is deployed in production. Let's say you're building some kind of, for the sake of an example, let's say you're building some kind of a phone-based app that recognizes things in the pictures that you take. Right? The first thing you want to do is start collecting pictures from mobile phones, right? And the reason you want to do it is you want to have your dev set distribution match the production scenario. Right? And it's important that you start with this step even before you start thinking about what your training data is. First define what your dev set is and then work backwards from there. Right? And you want to spend as much time as possible on collecting a dev set that matches the real world distribution as closely as possible. And by matching it as closely as possible, we mean that if your target set of users are, let's say, those who take pictures on phones as opposed to, say, tablets, or even better, if you know that your target set of users initially are going to be iPhone users versus Android users, then take pictures from the camera that your app is going to be used in, right? And then spend time on labeling it yourself, right? That gives you a real good feel for how your data actually looks and feels, right? So as part of this, collect data, preferably from the same devices, collected from the same devices that your model is going to get used, and label it. Right? Once you do this, you get your validation set or a dev set. The next thing you want to do is to define an evaluation metric. Right? So these two tasks of collecting a data set and defining some kind of an evaluation metric should be the first thing you do if you are, some kind of, if say you're the leader of an ML group or you're a product manager. The first thing you want to do is define what your dev set is, which should be a good representation of who your users or how your users are going to use the model, and defining a metric on this. And this metric will capture what's kind of important for you from this product. Right? And once you define this data set and evaluation metric, you've now effectively kind of painted a target for your team to go after. Right? These two should always be the first thing you define. And once you've done this, then comes the question of what the training set is. Right? So your training set could come from anywhere. Right? If collecting data is inexpensive, then you probably want to collect as much data as you can that mimics the production scenario and make that your training set. However, that's usually very expensive, right? Especially if you want to label your data set, that becomes really expensive because you probably want to use your own time, or you want to spend money and use crowdsourcing to label your data. And generally, labeling data can be very expensive. Okay? And which is why most of the time training data usually comes from a distribution that may or may not match your dev set exactly. Right? If you're working with images, let's say you're building an image classifier, you may want to use some kind of a pre-trained model, or use a very famous data set called the ImageNet for creating your training data. Right? And that can be very different from the use case where your model will eventually get used. Right? So So the next thing you want to do is now collect your training data. Right? And while you're collecting your training data, it should be as close as possible to the dev set. And generally, collecting the dev set, as I said, collecting more of the dev set itself can be pretty expensive. And here, you generally end up using some kind of an automated labeling, automated or noisy labeling. Right? And you may be surprised that noisy labeling or automated labeling can sometimes be extremely effective. And the idea there is that you kind of make up by quantity what you lose by quality. Right? And in fact, we've actually seen some examples of this in the course already. For example, in your homework 1, PS1, I think it was question 2. We looked at the case where you have some training set where the noises are, where the labels are noisy, where the labels are available, say, only for positive examples, and the unlabeled examples can contain both positive and negative. Right? That's one kind of data set that you may get by automated labeling, where you label only the points that you're very confident of and leave everything else as unlabeled. Right? And with that, you can still build models in a naive way and then apply some kind of a correction to get pretty good or decent models. This question?
When we did our assignments and research?
That's a very good question. So the question is, when we were doing homework or covering rest of the material, we spoke of first starting with some data set, some given data set, and split that into a test, validation, and train. Right? Why not do the same here as well? The reason why you want to think about it this way is because the approach that we discussed earlier of starting with some given data set and splitting it into 3 was quite common in a few years ago or a few decades ago when data was really scarce. Right? Now we are kind of in a situation where it's easy to collect data. It's difficult to label them, but it's generally the availability of data is quite abundant in a lot of use cases. Of course, there are use cases where data availability itself is low. For example, in healthcare, when if you want data about some rare disease, of course you're not going to have a lot of examples there. But for the most part, especially if you want to build some kind of a commercializable product, or then it generally tends to be around images, text, media, videos, etc. And generally it's quite easy to get lots of data, but labeling them is still hard, right? And in these scenarios, you probably want to have your model be tested against the kind of scenarios it's going to be deployed against, and have your test set performance reflect that reality when you actually put it in deployment, as opposed to take some data set that you obtained from somewhere and get a sense of generalization performance to that distribution, which could be very different from where your model gets used, right? So if you're thinking of deploying your model in a real world use case, always start from the way it is going to get deployed and work backwards from there.
Let's say have people or crowdsourcing click pictures and then label it. How reasonable is it to use scraping technologies that web scrape? Like if you want images, scrape the web for Google Images and then label it or somehow. And is that even legal to do from some these kinds of websites and scrape the web?
Yeah. So the question is, what about using scrape the web for images and do some kind of automated labeling? Is that even legal? Of course, if you're scraping copyrighted images, then you're actually subject to the terms that come with the license of that of whoever owns the images. So yes, legality is definitely open question, and you should answer that. In this course, we don't provide you legal answers for such questions, but you absolutely need to ask those questions and find out if the method that you're following is it legal or not. Absolutely, you should pay attention to that. And in terms of crowdsourcing, it is strongly recommended that the dev set, the labeling of the dev set, be done with as much care as possible, preferably by you and your team. And you could use crowdsourcing for labeling, say, your training data, but you want to be as careful as possible for labeling your dev set. Definitely, yeah. So we saw some of the automated what could happen under automated labeling with in PS1Q2. That's the positive only scenario. And once you kind of done your labeling, then you get into the question of how do we build a model that works well in production, right? Your goal should always be to build a model that works well in production, right? Which might seem closely related to a model that works well on your test set or model that works well on your dev set, but that is still a proxy. You should always aim for building a model that works well in production, right? And the way you want to work towards improving your model performance on production is to, let's say you come up with some kind of, let's say you decide to use, I don't know, SVMs or logistic regression. Doesn't matter what it is, right? Anytime you fit a model and you want to measure performance, you should always measure this breakdown. So first you have, say, human level performance. Right? And this human level performance, even though it is inaccurate, it is sometimes okay to think of this as a proxy for irreducible error. course, this is inaccurate, but it serves as a good proxy. We do have models that work better than humans in many examples. So in those kind of examples, this may not always work. But for the most part, if you're starting about building some kind of a model or some kind of a machine learning model for a specific product that you're working on, then human level performance on the dev set can work as a good proxy for irreducible error. Again, it's just a proxy. Yes, question.
So question about the automated noisy labeling. So what exactly is meant by that? So you're saying like you get data from already labeled data set or use some. So you started with the example of like recognizing something from images.
Yeah.
So you're saying like something like ImageNet or IMS or something like some already labeled data set. Use that as your training data?
Yeah, so the question is, what do we mean by automated labeling? Do we mean by using some data set that's already labeled? Is that what? So what we mean by this is, let's say you're trying to build a classifier for, let's say the prototypical example. Let's say you want to build a classifier given an image. Is there a cat in that image, right? And let's say you scrape the web, possibly that's illegal. We'll push that question apart, and you've collected a big data set. And in this data set, now we want to label this data set as those having cats versus no cats, right? And you want to have some kind of an odd. So first thing you do is collect a dev set that's going to match your deployment scenario, right? If your use case for your say mobile phone app is through pictures, then take pictures from, let's say, your phone, take lots of pictures and manually label those that have cats or not, right? And then comes the problem of collecting training data, right? Your data can be images that you scrape off the web, which may be completely unrelated. It may look kind of different from pictures taken in your phone. And now you want to do some kind of an automated labeling, right? And what does it mean here? You could perform automated labeling with some simple rules. For example, if the file name of the image has the word cat, then maybe it has a cat. So label it. Have some initial noisy labeling where you look at the file name. If it has the word cat in it, label it as positive. If it does not, label it as negative. That's very noisy. It probably works okay in terms of its degree of noise in it. You probably want to still perform some kind of a spot check to see, collect some random number of images from this labeled data set and see what fraction of them were labeled correctly with this automated rule, and maybe refine it a little further till it is, probably, say 90% accurate or 95% accurate.
Just to be clear, there's no actual machine learning happening in the automated labeling.
Yeah, you could use a simple model to do this automated labeling, but generally this automated labeling will use some kind of prior knowledge or domain knowledge to construct a rule-based. It's generally a rule-based labeling at the automated labeling stage. Right? So you want to break down the performance into the following parts, and then you have training performance. And when you're training, once you obtain this training data, you probably want to split it into an actual train set and what you might call as a train dev set, which is a fraction of your training set, which is distinct from the dev set that the goal of the dev set is to mimic the deployment scenario as well as possible. But your training data, you probably don't want to use all your training data for fitting the model as well. So within the training data that you've labeled, possibly with automated labeling, you still want to hold out a fraction of this, and let's call it the train dev set. Right? So train dev performance. It is sometimes common to take a fraction of your dev set and include it in the train dev set, and measure the train dev performance, and then measure the dev set performance. And this is the part that you manually labeled. and manually collected. Okay. And finally, we can talk about the deployment performance. And by deployment performance, what I mean is when you actually deploy the model into production and real users start using your model, what's the accuracy, what's the level of performance on the real world, right? And previously we were generally talking about train error and test error, or maybe train error, dev error and test error. But here, when you actually put things in or when you're working towards an actual deployment, you actually want to measure all five. There are these 5 different measurements that you're measuring. And the way you want to think of each of these different performance is the human level performance. As I said, you can think of it as a proxy for irreducible error. Once your model starts working really, really well, it might start performing better than humans, but we'll ignore those cases for now. And the gap between training performance and human level performance, the gap between these two, you want to think of this gap as a proxy to the bias in the model, right? The gap between training performance and human level performance, right? And similarly, the gap between the train dev performance and the training performance, you want to think of that as the variance in the model. Right? And now, similarly, the gap between the train dev's performance and the dev set performance, this gap, you can think of it as the error due to distribution mismatch. Distribution mismatch between dev and train. Right? And this distribution mismatch is because the training set that you obtained was generally obtained from a different process rather than starting with the process you used to mimic the test set, because this is too expensive. Right? And this is generally, therefore you can think of this as like, due to cost of collecting. This question?
What is train dev?
So the train dev is a fraction of the training data that you obtain, that you hold out as a train dev set.
Why call it dev?
Because we're calling this dev, so we just call it train dev, because it's just a fraction of the training data that you have, which is distinct from the dev set, which you manually collected and labeled.
So, but that train dev is going to be used somewhat like a validation set, right?
So the purpose of the train dev set is to kind of use it as a way to check if your model is overfitting or not. And the dev set is used to check if the model is going to work well in the deployment scenario or not, because the training data that you obtained was distinct or different from the potential deployment scenario. Okay? And finally, the gap between these, between the dev set performance and the deployment performance, is generally due to overfitting on the dev set. How can we overfit on the dev set? Even though we are not training on it, we can overfit on the dev set because we go through the cycle of refining our model and tuning our model to work better and better on the dev set to reduce this gap. And in a way, indirectly, due to our hyperparameters, we will inevitably end up overfitting on the dev set. Right? And once you overfit on the dev set, then your actual deployment performance can be pretty bad. Right? And to kind of summarize, our goal is to build models that work well in deployment. Right? This is our eventual target, You should never lose track of the eventual target, which is deployment performance. And all these other different measurements that you perform are a way so that you can perform diagnosis to improve the deployment performance. Right? These performance by themselves are not of direct interest. Right? You want to use these to diagnose where the error is coming from and go after and fix that error so that eventually we can do well on deployment performance. And the dev set, as you can see, can be subject to overfitting, especially if you evaluate your model performance on the dev set multiple times. You're going to reach a state where you've kind of overfit on it, in which case you might want to go back and recollect a new dev set because you've overfit on the old one, right? And that's pretty common too, where you recreate a new dev set because you overfit on the current one. And now, so given these, let's kind of go through a simple exercise to see what steps we can take to mitigate each of these. Right? Let's say you measure the human level performance and it's pretty low. What do we do? Well, if the human level performance is pretty low, like we've not even started, so there's no model in question here. You've collected a data set, and then you ask a human to measure the human's performance against on that task, and that is pretty low.
The accuracy is
Yeah,
low.
whatever metric that you come up with, accuracy or precision or recall, get better humans. Exactly. So if the human level performance is pretty low, then maybe go after a different problem, right? So because it's especially if you want to run some kind of diagnostics and characterize your errors, if the human level performance is pretty low on a task, then you can think of it as a problem where the irreducible error itself is very high. So it's kind of a bleak scenario. It kind of says that the problem is really, really hard. Right? Now, what if the human level performance is pretty good? It's within an acceptable range, but your training performance is low. Your training error is high. Right? But when you asked a human to perform the labeling or human to do the prediction, it was pretty good. What does this represent? It represents your model probably has high bias, right? And what do we do to address high bias? Increase flexibility of the model, right? So steps to kind of overcome this. Increase flexibility of the model. And how do we increase the flexibility of the model? Add features. And somebody said add more nonlinearities. So let's call it add features, or say add more depth if you're adding a neural network. Add depth, right? And I think someone said reduce regularization. Right? And let's say if you're using some kind of a kernel method, use more complex kernels. Right? So these are like standard approaches for fighting bias. If your model has high bias, then these steps will help you fight bias. And if you remember, bias is due to the inability for the model to represent like the true function or the best possible function. The best possible function or the best possible model will give you, the irreducible error. That's the best possible we can do. And the inability of our hypothesis class to represent the best possible model is called bias. And anything you can do to increase our model class to make it an even bigger class will help fight bias. Right? So all these things, adding more features, adding more depth, adding more width in your neural networks, reducing regularization, because regularization pushes your model towards zero. More complex kernels. All these are different ways in which we can fight bias. Now, what if the gap between the training performance and the train dev performance is more? What can we do there? Right? So what can we do here? Everything opposite. So yeah, so look for smaller models, right? And fewer features. Fewer features, increase regularization. Right? Increase regularization. Less complex kernels. And finally, there is one, most of these are like the inverse of the other. However, there is one thing that is distinct, which is collect more data. Right? Does getting more data help fight bias? Can it? Some say yes, some say no. So generally, you don't think of getting more data as for fighting bias. If your problem is that your training performance is much worse compared to human level performance, which means that the model that you have cannot even fit the training data that you have. Right? Which means the problem is that the model class that you have is too inflexible. Right? Getting more training data will not necessarily help your model fit that superset better than the subset that you had initially. Right? So if your training error is low, you kind of think of it as a proxy for bias, and the thing you want to do is not necessarily go and collect more data, but start increasing the capacity of your model, make it more flexible. However, if the gap between the trained error and the training performance is large, it means your model is doing really well in just fitting the training data, right? But it's not able to generalize well, which means you want to probably make it harder for the model to just fit the training data. So just collect more data, right? And with the hope that it generalizes better. Right? And what do we do if there's a gap between train dev and dev set? Change the rules for labeling.
Collect training data more systematically.
Right? So if the gap between the train dev and dev set is high, then it's an indication that there's a distribution mismatch between the dev set and the training set. And when there's a gap between when there is a distribution mismatch between the dev set and the train set, then obviously the thing that you want to do is minimize that difference in distributions. Right? One way to do it is to make the dev set closer to the training set, which would not be ideal, which would be kind of, it would be kind of stupid in a way. But instead what you want to do is make your train dev set be closer to your dev set. Right? And that you can do there are many ways to go about doing that. For example, you may want to spend some more money and collect more realistic data, label them and include them in your train dev and training set. You could do that. You could also do something more clever. For example, in your training set, maybe there's a subset of your training set that's somewhat close to your dev set. Maybe upweight those examples. Right? You could also maybe think of some kind of data transformations on your training set. For example, if your dev set is mostly images that are black and white, but your training set has a lot of color images, maybe run some filters and make them look closer to your dev set in some way. For this you need to use your creativity and somehow reduce the distance between your training distribution or the train dev distribution and the dev set distribution. And you want to reduce it by making this closer to the dev set, not the other way. This question?
Can you clarify why is it stupid to try to recreate your dev set in your training set? Because let's say like the goal of your product.
Oh, so just to clarify, what I meant was making this closer to your training set. By what I meant was replace some of these examples by examples from your training set. Right? You could potentially change this to make this closer to your training set, right? But that would be kind of against the point.
I mean, how can you change your dev set to make it similar to training? Like a dev set is what you get actually from the situation.
Yeah, that was my point. So you want to keep your dev set as it is and not change it.
But you would want to incorporate examples like as you observe them in the dev set from the training set, right? Like let's say the model you're building is to recognize faces or something like that, but you realize like since your training data was collected in a very noisy way, maybe it has a lot of images of vehicles or something. So you might want to like actually go and manually include more images that are similar to your dev set, right?
Yes, that was my point. Yes.
Okay, that was stupid.
No, that's not stupid. Yeah. Right. Okay. And what if the gap between the dev set and the deployment performance is poor? Let's say you've taken your dev set in as kind of a pure way as possible. You've sampled it randomly from the actual deployment scenario. You've labeled it, and you fit your model, and it's working well on your dev set, but it's not working well in real life. Right? What do we do then? Yeah, exactly. So it's probably time to refresh your dev set, right? It's a good indication that you've likely overfit on your dev set by going through this cycle over and over again. As we mentioned in one of the earlier lectures, the more number of times you measure the performance of your model against a dev set and tweak the model to improve the performance, think of that as your data set getting rotted, right? It probably means your dev set has rotted quite a bit, and it's time to collect a new dev set and start all over again. Right? And these two that we saw were some of the things that we saw earlier in the bias variance lecture. Right? In order to improve your model performance, there are a set of actions that you can take, and that set of actions contain contradictory actions. Right? So some of the action is to add more features, whereas another action is to reduce features. Right? These are all actions to improve your overall model performance. But in order to decide which specific action you want to take at this moment, it is very critical that you look at both the training set error and your dev set error in order to characterize whether the current problem that you have is a high bias problem or a high variance problem. Right? And only then, only after you've characterized whether the immediate problem is a high bias problem or a high variance problem, only then do you choose on the subset of actions that are meaningful and take that action. This question?
So you know when to stop when both the impacts, like human level performance minus training performance and training performance minus trained performance, when those both are equal, that's when you're like the best you can do is make both bias and variance equal.
Mm-hmm.
Right?
Yeah. So the question is, do we stop when this error vanishes and this error vanishes?
Is equal.
Or the gap between them vanishes and the gap between them vanishes, which means all three are equal. Right? So the question is, do we stop then? The answer is no. Your goal should always be deployment performance. Right? And all these are components that you can tackle with different action sets to help reduce.
Since the ways to mitigate both those problems are contradictory,
Mm-hmm.
you can only do one of them.
Yeah.
So I'm saying if you want to know whether you want to tackle bias or variance in your model, you have the best you can hope to do is reduce both of those difference in performances to equal. That's the best you can do, right?
Yeah. So there is some amount of let me get to that in a few minutes. What you want to do. The short answer is yes. you can always collect more data and drive your variance towards 0, and you can always increase a bigger, use a bigger model and drive your bias towards 0. So theoretically, if you have enough compute and enough data, you can drive both bias and variance to 0, right? That's one way to think of it. Yes, question?
What do we do when the training error is large but the error is small?
So what do we do when training error is large but the train dev or a dev error is small? Do you mean this gap is large and this gap is small, or the training error's absolute value is large but the train dev or the dev error's absolute value is better?
Yeah, it has a high bias but generalized.
So again, just to understand your question better, do you mean that the gap between train and train dev is small, or the train dev itself is less than the training error? Which of the two scenarios are you talking about? So are you talking about the scenario where the training performance has, let's say, 80% accuracy and the train dev is 79% accurate, which means the gap is small? Or are you talking about the case where the train dev is 85% accuracy, which means the performance is better than that? Which of these two are you talking about? The latter one, 85%. So this generally means that if the training dev performance is higher than the train performance, this generally means that there is still some kind of a there is still some kind of distributional mismatch, in the sense that maybe there is your train devs set is not a perfectly randomly sampled from the dev set. Maybe there is some bias in the way you've sampled the train dev set, and it could be that the fraction that got left out in the training set were harder examples, but this biased subset are easier examples. It's something like that. Generally, you don't expect this to happen. So if this happens, it probably means you want to reshuffle your train dev, merge them and resplit them again. Usually that's one way to go about it, because you should not expect, there is no reasonable reason for your train dev performance to be better than the training performance. Right? It means you're likely doing a bad job at even just fitting your training data, or there is some kind of a bias in the way you've split your train and dev set. Good question. Right? So now, there are what we've seen is there is some action space, and yes, question.
My question is, how do you measure deployment performance then? Because for everything else, you have a set of data that you kind of measure against. But for deployment performance, you kind of put it out into deployment already.
That's a very good question. So how do we measure deployment performance? And usually the way you measure deployment performance is to, generally there might be ways in which the feedback is implicit in deployment. For example, let's say if the action that if the prediction that you made was right, let's say the user ends up taking a certain path of actions, and you can kind of get this implicit feedback of whether your prediction was right or wrong. So sometimes you kind of get that automated feedback. In other scenarios, you want to make this prediction on the real data and then have somebody relabel them and measure the performance. Right? So collect some predictions that you made in deployment and have somebody label them just to see what fraction of them you got right.
So it's like another dev set, essentially.
Yeah. Think of it as another dev set if there is no implicit feedback. But sometimes there can be implicit feedback in your overall application. Let's say the user takes a certain kind of actions if the prediction was right. And in that case, you get like automated feedback. Good question. So here in our action space, we saw that some of these actions can be kind of contradictory with other actions. For example, add features versus fewer features, add depth versus reduce depth, reduce regularization versus increase regularization. Right? So some of them are kind of contradictory. and it's inevitable that you absolutely need to do a bias variance analysis to decide which of those actions you need to take. However, there is this action called get more data, right? So get more data can help fight bias, but you don't expect it to help. Can help fight variance, but you don't expect it to affect your bias in any way. But generally, getting more data is a pretty expensive step, and quite often, you need to answer the question of, does getting more data, is it going to help me or not, right? Getting more data, is it going to help me fight the variance in my model or not? Maybe the amount of data that you have is not sufficient, or maybe it is sufficient. How do you answer that question? So for that, there is this pretty useful plot that you would want to make. So the plot that you want to do is something like this. So this, think of it as fraction of data or data size green line is desired performance level, or let's call it this desired error level. And this axis is error, and this is a fraction of data, right? And you have your right. So what we do is we take the full data that we have and split it into smaller and smaller fractions, right? And with each of the small fractions, get the train error and test error, or the dev error, from that fraction alone, and then take a bigger set, get the corresponding train and dev error from the bigger fraction, and then get an even bigger set. So each of these here represents your data size increasing, right? So for simplicity, assume both your dev set and train set are proportionally increasing, and with each with increasing data size, plot both the train error, so this is the training error, and this is the test error. Right? In this scenario, the desired error level is somewhere over here. Think of it as human level performance. And by plotting your model performance of both the train and test error as you subsample your data, subsampling would go this way as you measure it on the full data. This kind of a model where the train and test performance come really close will tell you that collecting more data is not going to help you, right? Because the gap between the training error and test error is pretty small, and they're pretty close to converging. So if you were to collect more data and if you were to extrapolate these, they would probably kind of converge to this level, right? And the two are pretty close to converging. Right? So this is a scenario where collecting more data is not going to help you, right? Think of this as a high bias scenario. And for the question of collecting more data, the answer is no. Right? So collecting more data should not be the first thing you're thinking of in such a scenario. Right? However, in situations like this, where this is your desired error level, and your training error that's your training error, and let's see, I'm loosely calling this test error, but think of this as your train dev set or a dev set error. Right? In this scenario, collecting more data, so again this is fraction of data or data size. Here it would be reasonable to extrapolate this as this rising up a little further and this coming down a little more. Right? So if your plot looks like this, then you want to think of this as a high variance scenario. And for the question of collect more data, the answer here is yes. It is worth collecting more data. It is worth, depending on how much you value your performance, it may be worth spending more money and collecting more data. Right? Whereas if you are over here, your training error itself is a lot worse than the desired performance level, and your test error is matching your training error, which means you probably want to increase your model capacity, right? Use a bigger neural network, or use more features, or use a more complex kernel, right? So that first you bring your training error down, and Any questions on these? Yes, question.
Where do we decide the desired error level? Which part of the process do we set the desired?
Yeah. So the question is, how do we set the desired error level? And that is there is no common answer for that. That really depends on your application, and as the owner of the product, you need to decide what your desired error level is.
We want to bring it to zero.
So the desired error level, it may not always be possible to bring it down to zero, and the value to which you want to bring it to will actually depend on the metric of your choice, right? So if your metric is, say, accuracy, and your prevalence is very low, then this will be like a really low value in general. So it depends on your choice of metric. So intentionally, I've just called it error, but what the actual units here are will depend on the metric that you've chosen. Any other questions?
Shouldn't it be the answer to this question? Shouldn't it be like the desired performance? It will be upper bounded by human level performance, right? Like you wanted.
So the desired error level performance could be upper bounded by human level performance. Sure, it could be. Yeah. All right. Any other questions? Let's see. Are we done with the practical? A few more concluding comments. As I said, always, our goal should be deployment performance, right? Don't lose sight of the end goal, right? All the other measurements that we do are only to aid us in taking the right actions so that the deployment performance improves, right? It's very common to lose track and just focus on, say, dev set performance, or just focus on the train dev performance, but you should never lose track of the fact that your end goal is always the deployment performance. And while while deployment performance is your end goal, it is for tactical purposes, you want to measure the training performance and the train dev performance, or the training performance and the dev set performance, and look at those. And the reason you want to measure them is so that you can decide which action to take, right? But the action you're taking is with the goal of still getting good deployment performance, right? And this is where bias variance analysis kind of comes into picture, because with bias variance analysis, you can decide among these conflicting set of actions, which is the action that you want to take. If you blindly take some action that, let's say, increasing features is a good thing, and if you go ahead and increase your features, then that may be wrong, or the wrong thing to do if the problem that you're facing is high variance. Similarly, let's say you're at some you're getting some kind of a model, some kind of a performance on your dev set. You feel it is insufficient, and you go about just collecting more data to increase your dev set performance. And if you are in a scenario like this, where your test set performance was lower than the training performance, which means the test set error was higher than the desired level error, then collecting more data is not going to help you, right? And therefore, looking at the train error, looking at basically the breakdown of the performance at all these metrics is extremely crucial to decide what the next action that you're going to take is going to be. And another final advice is, in your homeworks, basically you've been implementing a lot of these algorithms, implementing gradient descent yourself, implementing GDA yourself, or neural networks yourself. Please don't ever do that in production, right? Don't implement the algorithms yourself. Always use some kind of a software package that somebody has already implemented and tested. Don't go about doing gradient descent by yourself if you want to build some kind of a real world application, right? That's totally the wrong thing to do. It's very important to implement neural networks yourself for the purposes of understanding how they work, right? But don't do that. Don't go about in some kind of an adventurous path and implement gradient descent yourself for your application. Yes, question?
So here in Silicon Valley, there are so many teams out there.
Yeah.
They are lots of Stanford people. They know all this stuff. Where does life go wrong? Like, what are the biggest pitfalls in your experience in the practical stuff?
Biggest pitfalls in practical stuff?
What do people do wrong? Like, so many teams fail.
So the question is, there a lot of people probably know this knowledge, but still lots of companies fail, lots of teams fail. Why does that happen? And I don't think there's a single answer to that, because first of all, you may know all the theory, but your execution may be poor, right? Even though you know things, you may not always execute them in the right way. That apart, there can be other reasons beyond your control. For example, even though your machine learning approach was correct, you may be solving a wrong problem for which there is no customer traction, right? So there are lots of other reasons that come into picture why teams fail, right? It's not always the technology that causes failure, right? So it's equally important that you go after a problem that that's kind of worth solving, and there are people or something that's valuable. If solving the problem is valuable, then it's good. But if your problem is solving a problem, even though you solve it well, if nobody's interested in the solution, then obviously you're like the team is going to fail. Not for machine learning reasons, but it's still a failure. All right. Any other questions on this before we move on to topics related to the exam? Cool. Okay, so the next thing I want to briefly touch upon, just for a few minutes, is to give you some kind of an expectation of the format of the final exam. We have posted some practice final exams on Piazza, which hopefully you've already had a look. however, use those practice exams as only for the purposes of getting access to a pool of questions, right? The format of the exam this time will likely be different, and in terms of the format itself, there are going to be so the format that I'm going to describe now. There is a very high probability that will be the format, but there is a small probability we may tune a few things. But more or less, what you can expect is the first question is going to be true or false, and there are going to be about 10 of them. The second question is going to be short answers, and there are going to be about 5 of them. The third question is you can call it a theory question. I'm just going to call it theory, right? It's going to be basically just math, and there are going to be sub questions where essentially it is a much longer proof for which we kind of guide you by breaking it down into sub problems, and you solve each of the sub problems, you would have effectively solved the full question. And the fourth one is you can call it theory / application, where again it's kind of a new problem setting that it's like a novel scenario for which you want to extend some of the ideas that you've learned in this course to this new setting, and there are going to be like 2 theoretical parts where you kind of derive whatever the update rules, prediction rules, etc., and a third programming component where you implement these rules in the starter code that we provide, and you execute it, and you get a plot, and you include the plot in your write-up. So this is going to be the structure of the exam. You can, I would say, expect it to be hard. It's not going to be long. So this is not we don't have 10 big theory questions or anything. It's much shorter than the homeworks that you've encountered with, but it's going to be it would be very necessary that you have a good kind of overall understanding of the course. You're good at the prerequisites, so things like probability, right, matrix calculus, linear algebra, and general things that we've covered throughout the course, like maximum likelihood, etc. It's very important that you have a good understanding of the prerequisites and also the important concepts from the course, like bias, variance, etc. But the specific the different set of questions. So basically, these 15 questions and these 2 questions, kind of more or less touch upon all parts of the course. Any questions on the format itself? Yes, question.
The only coding will be in the one part of the course.
Yeah. So the coding is going to be the last part of question 4. Yes, question.
Approximately how much hours do you expect it to take? Because there is takes actually 24 hours to finish.
It's hard to say. So there are these are true false questions and short answers. I mean, we expect you to say true or false in one sentence for an explanation, so 1 or 2 sentences for justification. Similarly, short answers, we expect you to derive an answer, but we only expect you to provide 1 or 2 sentences of reasoning or justification. So if you know the answers, you can finish 1 and 2 in a few minutes, right? But if you spend more time on this, you could potentially spend the entire 24 hours on just answering these. So it's very hard to tell how long it's going to take. So the format itself, if you know everything, we expect you to comfortably finish it in 3 hours. But if you're spending time on if you need more time to spend on each of these, you could potentially take more than 24 hours. So it's hard for us to set an expectation of how long it's going to take for a student. We could tell on average, but for a given student, the variance can be quite high. But think of this as like approximately 2 homework questions, right? And some, this again, they're just true, false, and short answers. So it shouldn't take too long. Any questions? Yes, question.
I mean, I can intuit that this would probably be low, but will you be answering Piazza posts during the exam?
Very good question. So this is going to be a take-home exam, which means we're going to post the exam on Piazza as a PDF, and you will write up your solutions, in tech or by hand, however, just the way you do your homework, preferably in tech, so that it's easier for us to grade, and you will post it on Gradescope like any other homework. During the exam period itself, we will disable Piazza, right? So even though the format is like a homework, it is not a homework, it's an exam, which means we will, you cannot talk to each other, you cannot collaborate, that's against the honor code. Collaborating on the exam is against the honor code. You can use any of the resources that you want, look at the course notes, look up, watch the lectures again, look at homework solutions. You're even free to look up the internet, but you cannot post on some, say, Stack Exchange and ask for somebody for help. But you're totally allowed to search the internet for any kind of questions that you may have, but no communication. Basically, by communication I mean no asking questions. But you can ask Google, but no asking any other human being. Right? During the exam, we will not help you in Piazza for things that you don't understand. You can create private Piazza posts, and if we think the question is already clear about it, we will not respond to it. Just like an exam room, if you have a question, ask yourself, would this be a question that I ask a TA in an exam room? And create a private Piazza post. If we think it's a valid question and if there is an ambiguity, then we will make a public post and clarify to everyone. However, if we think that the question is already clear about it and you have not thought sufficiently about it, then we will refrain from answering those kind of questions, or maybe we will tell you the question's already clear about it, something like that, just so that all the students obtain the same level of response from us. Does that answer the question? Okay. Yes, question?
When you say that Piazza will be disabled, will the responses and questions from throughout the before the exam throughout the quarter still be available, or will
yes, you can open Piazza and search for all the previous questions, but I think there is an option in which we can disable posting new questions, or there's some such feature in Piazza that we will be. Yes, question?
Regarding the math, is the prerequisite for the first week of review because of math, let's say, or does it cover everything we might want to know?
Yeah, so I would say for the math part of it, focus on matrix calculus, focus on probability, and of course linear algebra. If you're really comfortable with them, we expect these parts to be pretty straightforward. Yes.
Regarding the weight of grade on each problem, how would you? Is there anything?
I'm sorry, I didn't get the question. Can you please?
Weights grades on every problem.
Oh, so the grades. I don't remember it offhand, but it's something like 10, and I don't know, it's like 15, or 10, or 20, something like that. Yeah. All right, so with that, let's kind of rewind all the way back and start our course review. So the course review that we'll be doing some amount today and the rest on Wednesday is to kind of provide an overview or a second look at all the topics that we've covered, and also kind of spend some time drawing reference to the relevant homework questions that you've answered, because a lot of the things that you learned from this course were from lectures, but an even bigger chunk was from the homeworks, right? And some of you have probably gotten all the homework answers correctly and have understood them well. Some of you may have gotten the answers to the homework questions, but haven't really kind of understood like the big take-home messages from each homework. The homeworks are a huge part of the overall educational aspects of this course, right? And unlike many of the other math courses where homeworks are just assigned from some random textbooks, say problem numbers 17, 15, and 30 or whatever, in this course a lot of effort has been put into designing each homework so that it kind of complements the lectures and the overall learning experience. So we'll at least do a quick reference to each of the relevant homeworks and at least touch upon the take-home messages from each homework as well, depending on the order in which we are doing the review. All right. So let's jump right in. We're going to start off with supervised learning. That was the first section of the course. So in supervised learning, if you remember, the goal in supervised learning is to learn a mapping from X to Y, where you think of X as an input and Y as an output, and you're given pairs of X, Y's as a training set. Right? So in supervised learning, our goal is to learn a mapping from X to Y. And in order to learn this mapping, we have provided a training set S, and that training set is basically pairs of X, Y examples. I equals 1 to n. Generally, small n refers to the number of examples in our training set. Right? And Xi generally resides in a d-dimensional space, and this is usually called the input. Right? And output yi, if it's a real valued, then we call this regression. Right? If yi is either 0 or 1, we call this binary classification. Right? Yi could be integers 1, 2, 3, and so on, and this you can either call it count or Poisson regression and so on. Right? And the overall workflow for supervised learning was to start with a training set, and then run this training set through a learning algorithm, and the output of the learning algorithm was a model which we call the hypothesis. Right? So think of this as your training set could be X, Y pairs where Y is in 0 and 1. The learning algorithm was say logistic regression, and the learned hypothesis is the set of parameters that you got when logistic regression reached convergence. Right? And this learned hypothesis will now accept new examples X that it has not seen before from the training set and make predictions y. Right? This is the kind of workflow overview of what happens in supervised learning. Right? And the first algorithm that we learned was linear regression. Linear regression. Right? In linear regression, we assumed that the function h belongs to this parametric family where we defined it as h theta of x equals theta transpose x, where theta was some vector in Rd. Okay? And there's also this intercept term. We assume that x will include the intercept term, and theta will also the parameter in the theta vector that corresponds to the intercept term will be the bias term. Right? So sometimes to make it explicit, we call it d plus 1, and other times we just leave it as theta d and assume that it's in there. And in order to learn this parameter vector theta, right, we need to have a learning algorithm. And for the learning algorithm, we first define what is called as a cost function j theta, which is equal to sum over I equals 1 to n h theta of x minus xi minus yi square. Right? And this is also commonly called the squared error, where we want to penalize the difference between the predicted value and the correct value, and we want to penalize the square of that value and sum over all the squares of these errors. Right? And this we treat it as a function of theta, and we want to minimize this error by adjusting theta to the best possible value. Right? Another way to write this in vectorized notation is x theta minus y square. This question?
So is this the choice for the cost function because of the Gaussian or the negative log likelihood, or is this the other choice of the cost function you consider in practice?
Yeah. So the question is this cost function a consequence of the of assuming a Gaussian on the error term, or can you use other loss functions? So there are I'll be answering that shortly. The quick answer is that you can give this a probabilistic interpretation that had you assumed a Gaussian error term, then this would be the cost to minimize. But there are other interpretations for linear regressions as well. Yeah. Right. So what we want to do is find theta is equal to r min theta of j of theta. Right. And in order to we put hats on all estimated values, and in order to perform this minimization, first algorithm that we saw was gradient descent. Right. And in gradient descent, we start with a random initialization of theta and run this iterative loop where we repeat theta equals theta plus some learning rate alpha times yi minus h theta of xi times xi, and here we include a summation plus alpha times summation I equals 1 to n. So this is gradient descent, and we also saw a variant of gradient descent called stochastic gradient descent, where instead of this summation in each iteration, we randomly sample some example SGD, where we repeat theta equals theta plus alpha times, let's call it yk minus h theta of xk times xk, where k was sampled from the uniform distribution between 0 and n, or 1 and n if you, right. So sample a random example number, use that example to run gradient descent for that iteration, right. So that was stochastic gradient descent. So this was one way in which we solved linear regression using gradient descent. And then we saw these few other interpretations of linear regression. So this was using gradient based approaches, where the gradient descent based approach works for any cost function, not just linear regression. But in case of linear regression, we can also get the closed form solution for the final theta hat directly, right. The second approach was what we called as the normal equations for getting a closed form solution, right. And in the normal equations, we basically get x transpose x theta equals x transpose y, from which, if we assume invertibility of x transpose x, which for now we will assume x transpose x is invertible, we get theta equals x transpose x inverse x transpose y, or theta hat equals x transpose x inverse x transpose y, right. And this is kind of a pattern that you should tune your eye to look for, because this pattern we also saw that can show up in other places, like in factor analysis. In factor analysis, we saw that one of the parameter updates looked very close to linear regression, right? So that's the normal equation. And then we saw a few more interpretations of linear regression. So the other one was projection based, right? Projection. So so let's assume this is theta 1, theta d, and this is the parameter space. Right? And then there is this design matrix X. Right? This is the matrix. And run it through this, and we get an output space. This is y1, y2, call this yn. Right? So each dimension in the input, in the parameter space or the input space, corresponds to each parameter or each feature, and each axis or each dimension in the output space represents a different example. Right? That's because x takes input. X is in Rn by d. So it takes as input something in d dimension and produces output something in n dimension. Right? And here, because this is a d-dimensional space getting kind of up mapped to an n-dimensional space where we expect d to be smaller than n, the column space or the range of x is going to be a subspace of the entire output space y, where the subspace has dimension d. Right? So let me use some different colors. So the entire d-dimensional space will now get mapped to some subspace, right? And this subspace basically spans to infinity in all four directions, right? And it crosses through the origin. By definition, a subspace crosses through the origin, right? And this subspace is d-dimensional, However, for the given data that we have, the point y or the vector y may reside outside the subspace. Right? So this is the y that is given in the data. So we are given x, and we want to find a theta such that x theta equals y, and x and y come from the training set, and we want to find the best possible theta y such that x theta is as close to y as possible. Now the way we cannot always solve this exactly, right? X theta cannot always be exactly equal to y because y can reside outside the range of x. So instead what we do is solve x theta equals projection of y onto the range of x. Right? Instead what we do is project y onto the subspace spanned by x, and then solve x theta equals projection. Right? This cannot be equal because y can be outside the range, but this, by definition, the projection of y onto the column space of x can be solved. Right? And if you remember, the projection of y onto the column space of x is given by x transpose x inverse x transpose y, where this part is called the projection matrix. Right? So this is just the projection of y onto the column space of x, and once we have it in this form, when y is projected onto the column space, it is now, this x can be inverted in principle because there is a bijection between the input space and this column space. There's a one-to-one bijection, which means we can now, informally speaking, invert x from this projection for x. So you can cancel the x's and say x transpose x inverse x transpose y. Right? So this was the projection interpretation of linear regression. And finally, we also went over the probabilistic interpretation of linear regression. So in the probabilistic interpretation, we know that x theta will never exactly equal to y with this linear form. So instead we assume y equals x transpose theta or theta transpose x plus some epsilon, where epsilon is distributed according to a standard normal distribution with mean 0, and the variance, for now let's just assume sigma square, which is some unknown constant. Right? And now we can write this as the probability of, so with this we can write epsilon equals y minus x transpose theta or theta transpose x, which gives us probability of epsilon equal to probability of y minus x transpose theta, which is now a Gaussian distribution, should be 1 over square root 2 pi sigma square, where sigma square is inside the square root, times exponent minus, this has mean 0, so it would be this minus 0 square, which is just y minus x transpose theta square divided by 2 sigma square. Right? So this is just the standard normal distribution. And now if we perform maximum likelihood, that is basically find the parameter theta that maximizes this likelihood term so that it is, it conforms to a standard normal distribution as much as possible, we get L of theta is equal to log product I equals 1 to n 1 over square root 2 pi sigma square exponent of minus yi minus xi transpose theta square over 2 sigma square, right? And now we can take the log of the product as sum of the logs. So this gives us sum I equals 1 to n. Log of this term is some constant, and it's the same constant for all examples. So let's just call it, some c, plus log and the exponent cancel, minus yi minus xi transpose theta square over 2 sigma square, right? So we have some arbitrary constant that is common for all examples, and another arbitrary scaling constant that is common for all examples. So instead we can now write this as some other constant, say c prime plus 1 over 2 sigma square times the negative sum over I equals 1 to n yi minus xi transpose theta square. And now if you want to maximize the likelihood objective, so let me take the negative sign out over here. If you want to maximize this, that is the same as minimizing the term inside, right, because of the negative sign. And we can also ignore this 2 sigma square because it's just a common positive scalar across all examples. So arg max with respect to theta, L of theta is equal to arg min of theta of this sum over I equals 1 to n xi minus yi minus xi transpose theta square, right? So it's not by the reason why we cancel the 2 sigma square is because we are only interested in the arg min and not the minimum value, but just the theta value that gets us to the minimum, right? And the theta value is the same whether we include the scaling constant or not, right? And this is the probabilistic interpretation of linear regression. Probabilistic interpretation. Right? And here we saw basically the Gaussian distribution, and the main takeaway from this is that whenever there is a Gaussian distribution involved, there will always, that generally always corresponds to some kind of a squared error, right? Because you take the log likelihood, the log will cancel, this is a log of some constant, log and the exponent cancel, so maximizing the Gaussian likelihood is generally equivalent to minimizing the squared error of some term. Right? So that was linear regression. Any questions on linear regression? All good. And then after covering linear regression, we moved on to the first classification algorithm, binary classification algorithm, which was logistic regression. So in logistic regression, we are given logistic regression. Logistic regression, yi is now either 0 or 1, right? And in order to solve logistic regression, we kind of follow the probabilistic interpretation and do the same thing for logistic regression. In logistic regression, we assume that yi is sampled from a Bernoulli distribution, right? Bernoulli distribution, and probability of yi equals 1 is given by this 1 over 1 plus e to the minus theta transpose x, right? And initially we kind of construct this 1 over 1 plus e to the minus function, as a good reasonable guess, which we later rederive in GLMs as a natural consequence of assuming Bernoulli. But for now, let's just go ahead, where the predicted yi equals 1. So this will be our prediction, and this gives us the likelihood expression. So L of theta is now equal to 1 log of the product of I equals 1 to n of the Bernoulli likelihood, which is y hat to the power y hat I to the power yi times 1 minus y hat I to the power 1 minus yi, where y hat I is this, right? And all of this is a function of theta. And this allows us to write the objective of logistic regression as, so log of the product is the sum of the logs I equals 1 to n, yi log y hat I plus 1 minus yi log 1 minus y hat I, right? And for in place of y hat I, include this as yi here and here, and to solve it we use gradient ascent. There is no closed form solution for this, right? Run gradient ascent, and when you converge with gradient ascent, the theta value is basically the maximizer of this likelihood function, right? That was logistic regression. Any questions on that? Can I repeat the last part? So there is no closed form solution for recovering theta from this likelihood expression. Instead, what we do is run gradient ascent, and run gradient ascent till the algorithm converges, and when it converges, the theta value at the point of convergence is going to be the solution for maximizing the log likelihood of theta. There was another question?
Yeah, actually my question was, so I'm assuming if you do some sort of processing where you have a probability and you branch at a threshold value, is that something you consider in the algorithm?
Can you describe that a little more? I don't think I quite understand.
I'm a little confused. So you have the I thought that the probability that yi equal to 1 is just phi because yi is Bernoulli distributed.
Yes, the probability that yi equals 1 is just phi, yes.
But then
But the probability that yi equals 0 is 1 minus phi.
I agree.
Yeah.
In the third line of your exposition,
Third line is this one?
yeah. So you wrote the probability of yi is equal to 1.
Uh-huh.
My first question, should that be y hat I, or is that like a?
So this is the probability that yi equals 1.
Should be the probability that y hat I equals 1 by itself.
So this is just y hat. This will be y hat.
Okay, then should you have a threshold value saying that if y hat is above that, then yi equal to 1 or something like that? Or?
I see. So the question is, if I understood right, so here we are only talking about values. In order to make a decision of what our predicted yi is, should there be a threshold to say if this is greater than whatever 0.5, then the prediction is 1 versus the other. And the answer to that is logistic regression. So that's a good question. So logistic regression, even though we call it a classifier, it is actually just a probability machine. It outputs probabilities. And the way we convert these probabilistic outputs into decisions is using some kind of an additional threshold after the fact, right? So first we train a model to just output probabilities, and then using Basically, we saw this in the evaluation metrics lecture. You can choose different thresholds to optimize for different kinds of metrics. So you can choose a threshold for maximizing your accuracy or to maximizing your precision or what have you. Right? So that's generally done after the fact of choosing a threshold. Right? But logistic regression by itself just gives you probabilities. Right? Yes, question?
Just to be sure, like as part of our model, we assume that it exists a theta such as the probability of yi is given by this, and then we want to find a good theta to approximate the real one.
That's correct. So what we are assuming is that the probability of yi given xi can be represented in this form, and that there is some theta that gives us the right answer, and we go about and try to recover that theta. And the important thing to note there is that it is an assumption. We assume that probability of yi equals 1 can be represented in this form and try to recover it. And in one of the examples that we saw, I think it was homework 2, question 1. Let me. So in homework 2, question 1, we had this logistic regression stability problem, right, where you were given two data sets. On one data set, logistic regression would converge, and on another data set, logistic regression would never converge. It would go on and on. In that example, right, the data was perfectly separable, which means we could draw a line that perfectly separated the two classes. And in this kind of a scenario, the assumption that P of y equals 1 over 1 plus exponent minus theta transpose x. The assumption that P of y given 1, so this should be given x. Right? So we assume a conditioning over there as well. So let me correct it right away here. This is P of y given 1 given x. Right? So the probability y equals 1 given x can be represented in this form. In a way, this assumption is not met here, right? Because if you try to solve this, then the algorithm never converges and theta just goes to infinity. Right? So this assumption that the probabilities can be represented in this form is an assumption which may or may not hold. And in case of the perfectly separable case, this assumption does not hold. And in those cases, to handle such cases, we want to use regularization, where a regularization makes it kind of a well-defined problem, and we'll review regularization again when we go.
Follow up before you carry on.
Yeah.
I think so. The same question you were mentioning, they actually the method of visualization was to imagine that the two. This is the line that we plot the data. It passes through some of the points, and the points are so close together in two-dimensional space that it looks like it may not be passing through, may not be separating perfectly. But there's something about separating hyperplane in a higher dimension, in a higher dimension. So can you explain in which step of the algorithm the points are visualized by the parameters as existing in two different planes?
So in the data set that you have that was given, the data set where the model does not converge, you don't have to map it to higher dimensional space. The separating hyperplane can clearly separate them. Some of the points may be so close that in the graph they may look as though they are not separated, because in the plot each point is kind of represented by a small circle, and the circle may cross the separating line, and the line also has some thickness as a consequence of just plotting it. But if you look at the numerical values of each of the points, they are perfectly separable. Yeah, so you don't have to take it to a higher dimensional space for that example. It's just that the plotting involves thick lines, and so it does not appear to be perfectly separated or they're too close by. But if you inspect the numerical values, it is perfectly separable. So that was logistic regression, right?
Sorry, can I say before again?
Yes, question.
So I think there's a technical cure to this, which was to trail off the values for the alpha. I think to keep dividing it, make it proportional to 1 over t square, where t is the number of iteration.
Mm-hmm.
So some people say that theoretically it shouldn't converge, but when you implement it, it does. So can you provide some guidance?
Yeah, good question. So in that question, one of the sub questions was to recommend ways to fix this scenario, and one of the proposed ways was to make the learning rate of logistic regression decay over time at the rate of whatever 1 over t or t square or whatever. So in that scenario, it is kind of important to distinguish between convergence in code versus convergence mathematically, right? So if you were to decay the learning rate, and if you just decay to 0, then obviously the code will stop iterating, right? But the parameter value that you get is not necessarily the argmin or the true argmin, right?
Why not? Actually, I don't think I caught your P of y given x explanation really well.
So what I mean by that is, so we define this L theta equals some expression, right? And now in order to minimize this, we have this iterative algorithm where we say repeat until repeat. We have some condition, repeat until some condition, and you do theta equals theta plus alpha times yi minus h theta of xi times xi, right? So we are looping this. Now, if this is perfectly minimizable, which means if your loss function is well defined and has a well defined local minimum, then this algorithm will eventually reach some nearby point here, and theta hat will be this nearby point of the global minimum. However, in the problem that we had, so if this is theta, then the loss function actually looks like this, right? It reaches the minimum at infinity, right? So now the question is, if we run gradient descent on this, the algorithm will keep hopping over and over and over and over and over with each iteration. It keeps updating thetas all the way to infinity. Now the question is, what do we mean by convergence, right? By convergence, the mathematical meaning of convergence means recover the true theta. And in this case, there is no true finite theta for it to recover. So it's not even something that can possibly converge, right? It just goes to infinity. Now, however, here, if we have a condition, some arbitrary condition which evaluates to false, right? This computational algorithm will break out of the loop. Now, do we want to call that convergence, or do we want to call this mathematical notion of convergence where our estimate has gone arbitrarily close to the true value, right? So there are these there are these two different meanings of convergence. One is, does this computational algorithm stop, versus has our parameter estimate come sufficiently close to the true parameter, right? There are two different meanings, right? So by adding regularization, we convert this ill-framed problem into a well-framed problem, right? So regularization takes us from here to here, right? So that was logistic regression. Next, we studied a second algorithm for optimization called Newton's method. Right? So Newton's method is a root finding method where, given some function f, now let's call this x. Given some function f and some random initialization, right? Newton's method takes us to the nearest root. What do we mean by root? Root is an input to f such that f of x equals 0. Right? So Newton's method is a way where with some random initialization, Newton's method will take us to the nearest root of a function. Right? And we use Newton's method for solving our cost function by feeding the gradient of our function as the input to Newton's method, as f. So we set f is equal to L prime. Right? So the gradient function is used as the function whose root we are trying to calculate using Newton's method. And Newton's method basically gives us the update rule that theta equals theta plus 1 over, in this case, L double prime theta times L of theta. If theta is scalar, and in case of the vector valued inputs, there is the extension of Newton's method called Newton-Raphson method. Newton-Raphson, where the update rule is theta equals theta plus 1 or h inverse of theta times gradient of theta, where h is the Hessian, h of theta equals h is the Hessian, and this is the update rule. So a few things to keep in mind is that Newton's method is not a cost minimizing method. It is not a cost maximizing method. It's just a root finding method, which means no matter what kind of a function you feed it, it's plug and play. You don't ask Newton's method to maximize it or minimize it. It's doing neither. It's just finding the nearest root. Now, if the function, if L that you're using if L that you're using in Newton's method is a concave function, a convex function, right? So if this is L, then L prime of theta is going to be, the gradient starts out to be negative here, it becomes 0 over here, and it becomes positive later. So the gradient function is an increasing function. Right? So this is 0 and this is L prime theta. So it's an increasing function. Right? Similarly, if your L theta is concave, right, then L prime of theta is a decreasing function. Right? And Newton's method will just recover the point where the gradient is 0. Right? Because that's what it's doing root finding. It is not checking whether at this point the gradient is decreasing or increasing. It doesn't care. It just gets you to the nearest root. Which means if you feed in a convex function or a concave function, it will automatically recover the corresponding optimum point or the stationary point. Which also means if you feed a function that is kind of weird shaped, where it does not have a well-defined local maxima or minima or has multiple local maxima, it just takes you to the nearest stationary point. What that means is if you start over here, right, if your starting point is here, then Newton's method will maximize and take you to the nearest stationary point. If you start over here, if you start over here, then Newton's method will minimize it and take you to the nearest stationary point. And depending on the initialization, it was either a local maximization or a local minimization. Right? Newton's method only takes you to the nearest stationary point. This question?
And if you want to make sure you're somehow you got unlucky and you were at a global maximum, you can just actually find h of theta. Right?
So generally, you don't want to even use Newton's method in these unless you know that the function is convex or concave.
But I mean that itself is a very hard thing to do. Right?
Well, so generally you know that by by looking at the functional form, you can tell whether it's convex or concave. Like if you can show that the Hessian is positive definite, then you know it's a concave function or a convex function, and Newton's method is a good idea to use in those cases. If you're not sure, like for example in a neural network, you would never use Newton's method on a neural network because it might even be maximizing to a local minima for you, a local maxima for you.
But if you wanted to, then it should be positive semi-definite if it is convex. Is that correct?
Yeah, if it is convex, then the Hessian will be positive definite. If it's negative. All right. So it looks like we've run over time. Apologies for that. We will continue our review in the next lecture on Wednesday, and that will be the final lecture. All right. Thanks everyone.